In this module, we will be studying about the phenomenon of adsorption, Part 1. Students, you might know chromatographic analysis, softening of hard water, the cleansing action of soaps, and purification of water are all surface-mediated chemical processes. In these examples, the reactions occur at the surface. The branch of chemistry that deals with the study of the phenomenon that occurs on the surface or interface, that is, at the boundary separating two bulk phases, is known as surface chemistry. An interface is a surface that forms a common boundary between two different phases, such as an insoluble solid and a liquid, two immiscible liquids, or a liquid and an insoluble gas. The two bulk phases refer to pure compounds or solutions involved in the reaction. The interface is represented by putting a hyphen or slash between the two bulk phases involved. For example, solid-liquid or solid-bi-liquid. Surface chemistry is an important branch of chemistry, as a number of phenomena like dissolution, crystallization, corrosion, heterogeneous catalysis, and electrode processes occur at an interface. Let us consider two molecules, one present in the bulk and the other on the surface of the liquid phase. The situation for the molecule on the surface of the liquid is different from the one in the bulk of the liquid. The molecule in the bulk experiences a balanced force of attraction from all directions. However, the molecule on the surface is surrounded by liquid molecules of the same phase and also by fewer molecules from the gaseous phase. As a result, the molecule lying at the surface experiences an unbalanced force or some net inward force of attraction. Similar inward forces of attraction exist at the surface of solids. If you put solid charcoal in a closed vessel containing oxygen, you observe that oxygen molecules are attracted to the solid surface of charcoal. As a result, the concentration of the gas on the surface of the solid increases. The same reaction occurs if a liquid is put in a closed vessel containing gas. The gas molecules will accumulate on the surface of the liquid. This phenomenon of attracting and retaining the molecules of a substance on the surface of a solid or liquid, resulting in a higher concentration of molecules on the surface, is known as adsorption. The substance on the surface of which adsorption takes place is called the adsorbent, while the substance thus adsorbed is called the adsorbate. In the example that we just saw, the molecules of oxygen are the adsorbate, while the solid charcoal is the adsorbent. The reverse process, that is, the removal of the adsorbed substance from the surface, is called desorption. It can be brought about by heating or by reducing the pressure. The adsorption of a gas on the surface of the metal is called occlusion. For example, hydrogen is adsorbed on the surface of nickel or palladium. It is important to note that adsorption is a surface phenomenon. Hence, greater the surface area of the adsorbent, greater is the extent of adsorption. Thus, finely divided metals and substances with porous structure are good adsorbents, as they provide large surface area. Charcoal, silica gel, alumina gel, and clay act as excellent adsorbents. Let's look at an example of adsorption. Add some activated animal charcoal to a dilute solution of an organic dye, methylene blue. Stir the solution thoroughly and then filter it. You will find that the filtrate thus obtained is colorless. This is due to the adsorption of the dye on the surface of the animal charcoal. It is very important to note that adsorption and absorption are two different phenomena. Let's look at how they are different. The term adsorption refers to the attraction and retention of the molecules of a substance only on the surface of a solid or liquid, while absorption refers to the passing of a substance through the surface into the bulk of a solid or liquid. Adsorption is a surface phenomenon, where absorption is a bulk phenomenon, and the substance is uniformly distributed through the bulk. Let us understand this difference through an example. If a piece of chalk is dipped in a solution of ink and then broken, it is found that the actual pigment, the ink, is present only on the surface of the chalk and is not moved into the bulk of the solid. However, the solvent in which the pigment was present has uniformly passed into the bulk of the solid. Thus, the color component of the ink has undergone adsorption, while the solvent has been absorbed by the chalk. Another example is the action of water vapor. Water vapor adheres to the surface of silica gel. This is an example of adsorption since the molecules are retained on the surface of the adsorbent. However, if we place calcium chloride in a closed vessel containing water vapor, calcium chloride absorbs water vapor and forms hydrated calcium chloride. This is an example of absorption because water passes through the solid surface of calcium chloride. Sometimes, absorption may be followed by the dissolution of adsorbate in the adsorbent. This means that first, the material appears on the surface of the adsorbent and then passes into its bulk. When the two processes occur simultaneously, it is known as sorption. Dyeing fiber is an example of sorption. Dyes get adsorbed as well as absorbed on cotton fibers. Let us now look at the thermodynamic aspect of adsorption. Adsorption is accompanied by a decrease in the residual forces of the surface. This implies that some energy is released when the molecules of the adsorbate get attracted to the surface of the adsorbent. That is, the change in enthalpy, delta H, is negative for the process. Also, the degree of freedom of the adsorbate decreases upon adsorption, which means that the change in entropy, delta S, is also negative for the process. We know that for any thermodynamic process to be spontaneous, the Gibbs free energy change, delta G, must be negative. The Gibbs equation is delta G is equal to delta H minus T delta S. So, delta G can be negative if delta H is sufficiently negative. Since minus T delta S is positive for the process of adsorption, when delta H becomes equal to T delta S, or when delta G becomes 0, the adsorbate and the surface reach a state of dynamic equilibrium. Let us further study about the phenomenon of adsorption. Let us first recall some details about adsorption. You already know that at a constant temperature, the adsorption of a gas increases with an increase in pressure. At a low temperature, the physical adsorption of a gas increases rapidly on increasing the pressure. On the other hand, at high temperatures, the increase in adsorption is relatively less. Let us learn more about the effect of pressure on the adsorption of a gas at a particular temperature. Adsorption is basically an equilibrium process. In order to understand the equilibrium process, consider an adsorbent and a gaseous adsorbate in a closed vessel placed at a particular pressure P. It is observed that due to adsorption, the pressure of the gas decreases initially and becomes constant after some time. This indicates that a state of equilibrium has been attained. Once equilibrium is reached, the rate of adsorption becomes equal to the rate of desorption. The extent of adsorption, that is, the quantity of gas adsorbed per gram of the adsorbent, is expressed as x by m, where x is the mass of the gas adsorbed and m is the mass of the adsorbent. The variation in the amount of gas adsorbed by the adsorbent with the variation in the pressure at a constant temperature can be expressed by means of a curve. This curve at a constant temperature is called the adsorption isotherm. Freundlich in 1909 was the first to propose a mathematical relation for an adsorption isotherm. He gave an empirical relationship between the quantity of gas adsorbed by a unit mass of a solid adsorbent and pressure at a particular temperature. The relation can be expressed as x by m is equal to k multiplied by p to the power 1 by n, where x by m is the amount of gas adsorbed by a unit mass of the adsorbent. N and K are constants and P is the pressure. This relationship is generally represented in the form of a curve and is known as the Freundlich adsorption isotherm. In this adsorption isotherm, x by m reaches its maximum value at point Ps. In other words, the extent of adsorption is highest at this point. It can be seen from the curve that even if the pressure is increased beyond Ps, the extent of adsorption remains the same. This is called the saturation state, and Ps is called the saturation pressure. The saturation state is observed when the adsorbate forms a uniform molecular layer on the surface of the adsorbent. If you look at the curve carefully, you will observe that at a low value of equilibrium pressure, part OA of the curve is nearly straight and sloping. Therefore, for part OA of the curve, the relationship between the pressure and the quantity adsorbed can be represented by the equation x by m is directly proportional to p to the power 1. Observe the curve beyond point P. That is, at a very high pressure, x by m is independent of the value of P. This is represented as x by m is proportional to p raised to the power 0. Let's now look at AB part of the curve. For this part of the curve, x by m lies between p to the power 0 and p to the power 1. In other words, in the intermediate range of pressure, x by m depends upon p raised to the power 1 by n, where n is a positive integer. At a particular temperature, n and k depend upon the nature of the adsorbate and the adsorbent. Note here that 1 by n has a value between 0 and 1, and the probable range is 0.1 to 0.5. Now, when 1 by n is 0, x by m is constant, and it is in this part of the curve that adsorption is independent of pressure. On the other hand, when 1 by n is equal to 1, x by m is equal to kp, which means that x by m is directly proportional to p. In other words, adsorption varies directly with pressure in this part of the isotherm. If you compare the adsorption isotherm for a gas at different temperatures, you will observe that at a particular pressure, there is a decrease in physical adsorption with an increase in temperature. The Freundlich adsorption isotherm can be validated by taking the logarithm of the isotherm equation. Taking logarithm of both the sides, the equation becomes log x by m equal to log k plus 1 by n log p. This equation corresponds to the equation of a straight line. Y is equal to mx plus c. So, we plot a graph between log x by m and log p. If it is a straight line, then we say that the Freundlich adsorption isotherm is valid, otherwise not. Note here that the intercept on the y-axis is equal to log k, and the slope of the straight line gives the value 1 by n. It has been observed that adsorption from solutions follows generally the same principles as laid down for the adsorption of gases. Let's verify this with an experiment. Take a litmus solution and add charcoal to it. And then shake it thoroughly. You will observe that after some time, the litmus solution turns colorless. This is because the dye of the litmus solution is adsorbed by the charcoal. Similarly, when activated charcoal is added to a solution of acetic acid in water, part of the acetic acid is adsorbed by the charcoal. And the concentration of acetic acid in the solution decreases. The amount of acetic acid adsorbed per gram of charcoal depends upon the surface area of the adsorbent, the temperature of the solution, adsorbate concentration in the solution, the nature of the adsorbate and the adsorbent. Though the exact mechanism of adsorption from a solution is not known, some important observations have been made for adsorption in solution. Temperature plays a major role in determining the extent of adsorption. As the temperature increases, the extent of adsorption decreases. Secondly, the extent of adsorption increases with an increase in the surface area of the adsorbent. Charcoal, because of its highly porous nature, provides a large surface area and hence is the most preferred adsorbent in industry and pharmacy. Thirdly, as the concentration of the solute, that is, the adsorbate, increases in the solution, the extent of adsorption increases. Lastly, the nature of the adsorbate and the adsorbent governs the extent of adsorption. That is, the nature of the bonding between the adsorbate and the adsorbent depends upon the species involved. Variation in the extent of adsorption with the concentration of the solute is usually represented by the Freundlich adsorption isotherm. The equation can be represented as x by m is equal to k multiplied by c to the power 1 by n, where x by m is the amount of solute adsorbed by a unit mass of the adsorbent, and c is the equilibrium concentration when adsorption is complete. Taking logarithm of this equation, we get log x by m is equal to log k plus 1 by n of log c. This equation also corresponds to the equation of a straight line y is equal to mx plus c. If the graph between log x by m and log c is a straight line, then we say that the Freundlich adsorption isotherm for solutions is valid. The Freundlich adsorption isotherm for solutions can be tested experimentally too. Let's take the example of the adsorption of acetic acid on charcoal again. Take equal volumes of acetic acid of different molar concentrations in different flasks and add an equal amount of charcoal to each flask. Shake the contents in the flasks and keep for some time. The final concentration of acetic acid is determined by titrating the resulting solution against a standard solution of sodium hydroxide. From the difference in the initial and final concentrations, the value of X, the amount adsorbed, can be calculated. The results obtained from this experiment also support the hypothesis that the extent of adsorption increases with an increase in the concentration of the solute. The validity of the Freundlich adsorption isotherm can, therefore, be established.